I'll start. So thanks to everybody for coming today. So it will be a double seminar today. We'll start with Ilfa Gabitova, who is from Al-Farabi Kazakh National University in Kazakhstan. So for those who were there last year, it was a really nice conference there in Almaty, and so we are continuing, well, the great work done in Kazakhstan. So please, Ilfa, go ahead and present what you have been doing those last time.
Thank you very much. Thanks for inviting me. Hello, everyone. And so today I want to talk about my recent research. It is on system called HD698, which combines recent high-resolution spectrometry results from interferometry and new radiative transfer modeling of the system to constrain its physical parameters. The system itself is a member of this kind of new emerging class within B binaries, where the companion of a B star, the second star, is spectroscopically visible. Here is a list of my colleagues, all the great people who made this research happen. And the first chapter is orbital motion. So let's see. Here, the upper plot is absorption lines and the bottom plot is H alpha region. So we can see that all of the lines, they show the same motion, and even emission in H alpha is visibly dominated by this motion. It has quite a large amplitude. And we were able to confirm for this system the new claim that this motion belongs to not to a B star, but to the companion star. The dominating motion of the companion star is shown in blue dashed line. And as a little spoiler for the next slide, the red dashed line is showing the B star's motion, which cannot be seen visibly on these plots, but it is there. Here on this plot, the two RV curves that are contrafaced, so the black circles are from RVs of absorption lines, and triangles are from RVs of the wings of H alpha line, which approximates the motion of the B star. And this system was luckily resolved with interferometry this year. With the parameters published in this study, we were able to get a full orbital solution for the system. As you can see, the masses are resolved for both components, and mass of the companion is very well constrained. It is kind of high for a companion of a B star. And we were also able to determine distance, which differs from Gaia's distance by like 180 parsecs. So the next step was modeling of the SED done with H-dust, radiative transfer code. So here on this plot, it is a plot of best fit solution. The black dots show observed data, and the pink line is the best solution model, which is a three-component model. So it includes contribution from a companion star, which is shown in green. It includes B star plus plus circumstellar disk, which is shown in yellow solid line, and And I also show here light emitted from the disk, a yellow dashed line. The model agrees with the data pretty good, and we were able to get a nice set of parameters for the companion star, which is as follows here. The B star was assumed from Geneva evolutionary tracks, and so from the fitting of SCD we got companions parameters, and we can also compare it with other previously published systems which show the same traits as HD698. So we can see here that from this class of B stars plus bloated companions or plus pre-subdwarfs, this new system is the coolest, and it has the biggest radius. So let's put it in a context of population of B binaries. Here, this plot shows, this plot is from recent work that researched V658 CAR, which is the second confirmed B+sdB binary. Second to Kappa Draconis, here there are two BSDBs, and the green is the population of known B+sdO binaries. And where would this new class of B plus bloated companions fit in? Let's see. So this is the same plot as on the left. The green is still B plus SDO, and the two BSDBs are shown in orange. The blue circles are the systems that were previously already known as B plus bloated companions that I've shown on the previous slide in the table. And the pink one is HD698. So we can see that there are three distinct groups of B binaries on this plot. And this new class, they're kind of hanging with their own, waiting to evolve into probably green population. And even within this class, HD698 kind of stands out. The B star is pretty much where you would expect a B star to be. And the companion is farther from other non-companions to the cooler side. So we don't yet know. Is it because it is younger than those systems, or maybe because it is more massive initially, inherently? And there are, so the evolution status of this system is still an open question, and it sort of boils down to the problem of chemical abundances analysis that we plan to do in the future. But for now, just to show you the gap in our current research, the lines were fit very badly. So the best fit model from the SCD does not reproduce lines very well, neither Balmer nor absorption lines. Here we can see helium, very underpredicted by the model, and slightly better line of iron. But still a long way to go. So, well, this is it. Thank you very much.
Thanks a lot. And thanks for the colors, which are really appropriate for your last light, of course, for the time being. So, if anyone has a question, please don't hesitate. Who wants to be first? We have time for a few questions before going for the second part.
Hello, this is Douglas Guys.
Yeah, sure. Go ahead.
Hi, what a lovely result. Thank you very much for sharing it. This is a beautiful system and lots of interesting questions. I was really intrigued about the H alpha plot you showed. I think it was maybe slide 3 or slide 4, where you showed the orbital variations in H alpha. Yeah,
Mhm.
that's it. Slide 4 there at the bottom where you can see H alpha, and it looks like there are, looks like to me, several patterns of what look like upside down V patterns down in the H alpha that apparently appear to follow orbital motion. And I was struck by this. It looks very similar to what Drew Chodnowski found in, I think, the 2016 paper on HD 55606. And in that paper, it's argued that when you see features that start at large velocity in H alpha and then migrate to low velocity, that might be a signal of spiral arm structure in the disk of the BE star. So to me, it's very interesting. I hope you might have a chance to explore that a bit. Thank you.
Thank you. If I might comment a little,
Sure,
because
sure. Go ahead.
H alpha in this system is indeed very curious. So we attempted in another small paper to isolate the central emission peak that traces the orbital motion of the companion star. And when we do it and we remove it from the H alpha profile, it becomes double peaked. And we reconstructed the matter distribution with Doppler tomography, and it shows tangential signs of maybe emission associated with a secondary star, not just with circumstellar disk. So it is indeed a cool system.
We also have a remark by Greg. Do you want to voice it, Greg? Okay, so if not, okay, if not, I will just read what he put in the chat. So, mentioning that Plaska star looks similar to this HD 698, but of course with higher mass. And he was wondering if there was a magnetic field search for this case. Did you do spectropolarimetry for this object?
Oh, not yet. But it might be in the plans, and in the future. But yeah, it's very interesting suggestion.
Okay. I may ask a last question. I was wondering about the difference with Gaia. Is it, in fact, just because the Gaia distance is wrong? I mean, we know that, in some cases the Gaia distance has problems, and you can look at some of the parameters showing that it is indeed not very good. Is it the case here, or is it another problem?
So the Rube, the sort of error parameter of Gaia, was marginal, like right on the border where you can doubt it. And in the paper, we ran models with both distances to compare. So Gaia's constantly shows higher chi-squared. So I think it's safe to assume that the dynamical distance is more trusted here.
Okay. Great. So if there is no urgent question, we'll go to our next speaker. Ilfa will stay there. So if you still have questions after Thibault seminars, of course, don't hesitate. So Thibault is from Garching, so that's I would say closer to what we usually know. Um, so this time we will still be doing mass transfer, but this time we'll look about the efficiency of mass transfer. So Thibault, you have the floor.
Thank you for the nice introduction. And the talk just before by Ilva was actually a pretty good introduction to types of systems that we'll be looking at today, since HG 698 is kind of a precursor, where I'm looking at a slightly later stage in strip stars. And so the headline summary is that we found pretty strong evidence for efficient mass transfer in post-interaction binaries. And so I'll start with the context. So I'm sure most of us are familiar that massive stars in particular are very commonly found in interacting binaries. And this leads to a variety of astrophysical phenomena that are not found in single stars. And so it's pretty interesting to try to understand how these stars can interact. And one of our main uncertainties in understanding this process is how mass transfer works. Since this is very complicated and there's a lot of physics involved, we want to try to understand that better. And so just to introduce the types of systems we'll be looking at, I made a very crude PowerPoint animation. I hope you excuse that. But we have two zero-age main sequence stars that orbit each other. During the main sequence, the more massive star evolves faster, where it grows a helium core at its center. Eventually, right after the main sequence, it'll expand a lot and overflow its Roche-lobe, at which point there is mass transfer, where it donates its envelope to the companion star. And the companion star spins up by gaining angular momentum with this mass. And then there's some amount of mass that has left the system, either in a circumbinary disk or left the system completely, and we don't really know how much. And so the prototypical system is pretty well known. It's Phi Persei, which consists of about a one solar mass strip star, which consists of the helium core of the original donor star with some amount of hydrogen envelope remaining, and a rapidly rotating Be star, which is about 10 solar masses. And there's some amount of mass that's left the system, but we don't really know how much. But we love to know how much mass was actually kept by this companion. And for that, we'll try to understand it first from a theoretical point of view. And so simple mass transfer is modeled commonly by two different approaches. One is that an approach that looks at the thermal timescales of both stars, which is kind of the characteristic timescale by which stars can handle mass gaining or mass losing. And this tries to avoid a contact scenario, which kind of keeps the companion star in check. Second model is the rotational limited model, which says that, okay, as mass is thrown from the donor to the accretor, this accretor should gain a lot of angular momentum and spin up very quickly to the point where the centrifugal force is balanced by the gravitational force. And at that point, accretion should stop. And this is predicted to happen after only a small amount of mass is accreted. And then on the observation side, it's quite difficult to identify these post-mass transfer systems, especially in these extreme mass ratio cases. And because of the difference in brightness between these two stars. And up until a few years ago, the only system was Phi Persei, which had accurate dynamical masses, and it was found to have accreted at least half of the transferred mass. And so there's this tension between theory and observations. One says it should be a small percentage of accretion. The other says it should be at least half. And so let's try to, whenever there's tension, there's a good area to do a research project. And I'll give a small spoiler, but we'll make this tension even worse, actually. We're not going to resolve it in this talk. And so the way that we're going to try to examine this further is using a very big new sample of similar systems, so suborbital B-star systems, that have been characterized using Fourier spectroscopy, and we have partially dynamical masses using interferometry, which gives us very accurate mass estimates, and it's so precise that we can actually resolve the orbits of this subdwarf going around the B star, which is very powerful. And this gives us precise masses, which allows us to better constrain the initial states of the systems. And so I'll now briefly explain the method by which we can constrain the mass transfer efficiency using just the current day observed masses. And so in this evolutionary diagram, you can see the birth configuration at the top and the present day system at the bottom. And the way that we try to infer anything about the initial state is we use our knowledge of single star evolution. So we know that right after the main sequence, the size of the helium core roughly correlates 1-to-1 with the initial mass of the star. So more massive stars lead to more massive helium cores at the end of the main sequence. This means that if you know the mass of the helium core, you can just kind of read off what the initial mass should have been, roughly at least. And if you know the initial mass, then you know how much mass it has lost. And in a purely conservative case, where this companion star would get all of the mass that the donor lost, we have the following configuration, where the companion star should have been initially about 3 solar masses. In a non-conservative case, which is where the companion star did not accrete all of the mass that the donor lost, but some mass has left the system, and we don't know how much. But if it doesn't accrete all of the mass, then to still explain the present-day masses, it must have been more massive initially. Here it should be 7.4. But note that there's a fundamental evolutionary constraint. There's this upper bound to the initial mass of the companion star, because if the donor star, if the companion star would have been more massive than the donor, then it would have evolved faster, and it would have transferred mass to the other star. But that's not what we see. So we have this upper bound on the initial mass of the companion, which leads to a lower bound on the amount of mass it must have gained to still explain the present-day masses. And so this is how we find a lower bound on the mass transfer efficiency, which was done for Phi Persei here and by Ono Pols in 2007. But note that this method actually doesn't depend, or it only depends on the present-day masses of the systems. So we can not only do it for all of the new systems in our sample, but we can also do it for any theoretical combination of such a system. And so that is what we did in this figure. So on the x-axis, we have the mass of the strip star, and on the y-axis, we have the mass of the accretor. In these gray and white points and arrow bars, you can see the observed masses of the systems in our sample. In background color, I plotted the minimum fraction of mass accreted, which is derived using the method I just explained earlier. And what we see is that Phi Persei has a relatively high lower bound on the mass transfer efficiency, which was found before. But we see that the other systems in our sample also have really high constraints. So Phi Persei, which could have been an outlier if you had only one such system, actually seems to represent a larger sample of systems, where all of these systems should have had some conservativeness in their mass transfer. Now, there are some outliers, specifically HR 2142 at the top there, but it also has large error bars. And if we did an updated analysis using spectral fitting and combining that with the estimates from interferometry, we get something that looks a lot closer to the other stars in the sample. And then there's on the left is HR 6819, which seems to be an outlier because A follow-up study by Ana Pico examining just this system found it very, very hard to explain the masses, even varying all the assumptions according to angular momentum loss and initial states. So this seems to be a hard system. So we'll ignore it for the rest of the analysis, but the rest of the 14 systems we do trust pretty well. And so if instead of just plotting the lower bound, we plot the allowed range of mass transfer efficiencies for each of these systems, we get something that looks like this, where the allowed range is bounded by below by our lower bounds. There's a 1 sigma range plotted here in transparent, which allows for the observational uncertainties. And then these black bars, which is kind of our best guess, which allows for incomplete stripping of the star during binary interaction, which changes the initial mass to strip mass relation, and it actually increases our lower bounds. And it's bounded by above by setting some reasonable limit on the critical mass ratio, below which there shouldn't be stable mass transfer. And then if we compare this to the theoretical predictions at the top, we see that the rotationally limited model, which is commonly used in detailed binary evolution models, only predicts a very small amount of accretion. This is an option used in the Mason stellar evolution code, and then also used by Poseidon, the population synthesis code, and large grids of the bond group. But this model is in very strong tension with all of our allowed ranges for these systems. Second theoretical model is this thermally limited model, which compares the thermal timescales of two stars and limits accretion if they differ too much. This is an option commonly used in rapid population synthesis, but you see that it kind of predicts this bimodal distribution, where it's either below 20% accretion or either fully conservative accretion. But most of our systems have good support between this 30 and 70% range, which doesn't have much support from this thermally limited model, which is why we also interpret tension here. And then what's interesting is that if you just put a constant value for beta, like it's 70% here, let's say, which is not expected to capture the physics at all, and is commonly used as just an approximation to set just one value, it could actually explain these systems. Now, I'm not saying this is what it should be, but it's just interesting that such a simple method could actually explain these systems. And so now we can discuss, well, how can stars actually accrete so much? There's a few possibilities that we thought of. One is that it could be tides, but these stars are too far away for tides to have had a strong effect in their evolution. There could be some magnetic fields that explain this, but up until now, I don't think there's been large-scale magnetic fields detected. And then the most plausible explanation here is that there's some kind of viscous accretion disk that can handle this angular momentum efficiently, which theoretically shouldn't limit accretion. There shouldn't be a limit to accretion for these companion stars. And now this compares to other work pretty nicely, because we find support for our findings at a lower, higher mass and at earlier stages. So looking at blue stragglers, for example, we also find relatively conservative accretion. Looking at these puffed up strip stars, they can also be used to find pretty conservative accretion, and then X-ray binaries have a similar finding. Now, in contrast, if you look at much higher masses in Wolf-Rayet plus O-star binaries, it seems to be that mass transfer is less efficient. And combining all of these, this implies a mass dependence of the efficiency, which is also seen in hydro simulations, actually, where if you have these high masses and huge mass transfer rates, then it's very hard for mass to stay inside of the system. And so there's some other interesting work also looking at stripped envelope supernovae, looking at the luminosity of the companions and trying to infer accretion limits using this, and also algols. But since the mass transfer is still currently ongoing, it's a bit more difficult to get strong constraints on this. And so then we can talk about the implications about from this result. And because it affects the stable mass transfer channel, it has a huge impact on the final masses and orbits of any system that goes through the stable mass transfer. Additionally, it'll affect the properties of these companion stars, so of mass gainers. If you accrete like 50% of your initial mass, your internal structure is going to change a lot, and therefore your evolution. And then, of course, any later stage systems after this this evolutionary stage will also be affected. And so, for gravitational waves, for example, right at the end of the lives of stars, there's been previous studies that have shown if you increase the mass transfer efficiency, you can increase or drastically increase the local merger rate of binary black holes, which is another reason for why this finding can be important. And so, in conclusion, we found predominantly efficient mass transfer in the 2 to 9 solar mass range. We find tension with these very common mass transfer models, and we find strong implications for the stable mass transfer channel. And I leave you with a picture of Seneca in this strip star, because Seneca is the founder of Stoicism, and these binary stars can kind of be seen as the original Stoics, where whatever life throws at them, they take what they get. Thank you for your attention.
Thanks a lot. Thanks a lot, Thibault. So, any questions for Thibault? Lots of blows, like for Ilfa. Thanks. So, anyone wants to start questions? I do have one. I was wondering if you change this efficiency, um, do you think that at some point we will have orbits which will be still wide enough to correspond to what we see in some of those BE binaries, which are, I mean, it's not so close, right? We still have like hundreds of days in some cases.
Yeah, there is some dependency on the mass transfer efficiency, depending on for the final periods. And this then also depends on what you assume for the angular momentum loss during this mass transfer process. But we tried various reasonable assumptions for this angular momentum loss, and we found solutions for almost the whole range of mass transfer efficiencies. So it doesn't seem to be that limited in that sense.
Thanks a lot.
Thank
Anyone
you.
else? Don't be shy. Trying to see if someone raised a hand. Any additional question for Ilfa also? Don't forget. So we have both Ilfa
Hello, this is
and
Doug Guys
yeah,
again.
Doug,
Thibault.
go ahead.
Thank you very much, Thibault. Beautiful work and analysis. Very lot of interesting consequences to think about. Could you mention something about consequences for the mass gainer in terms of subsequent lifetime and and evolution having accreted so much material?
Right, of course, because it would accrete so much during the main sequence, its lifetime would be much shorter. In some cases, maybe half of what it would originally be if it had not accreted anything. And this will change the supernova delay times, for example, and possible future evolutionary stages. But in terms of actually quantifying how much this changes, we did not yeah, look into that. But I'm sure there's other work that have already explored this.
Okay, thanks.
So I
So
can
maybe
ask one.
one last thing.
Oh, go
Sorry.
ahead.
Oh,
Go
go ahead, Thibault. And
I was just going to mention that I also plotted uh, Ilfa's system in this plot because as long as the masses of these puff drop stars don't change, you can still derive an efficiency constraint. But it happens to land right at the bottom of this plot, which doesn't say that mass transfer should be non-conservative, but it just says that with this method we cannot place constraints on it.
okay,
Yeah.
John.
Yeah, nice talk. Yeah, I
Thank you.
followed your paper closely. So my talk's a little, or my question's a little broad, but as an observer, what can we do to help address this problem? Do you want a bigger sample? Do you want a more diverse sample in terms of the masses of the two components? Better observational constraints on individual systems?
Right, yeah, that's a great question. Thank you. There's a lot of things that can be done to improve our understanding here. Um, one thing is that this plot really clearly shows is that the observational error bars on the masses of these systems directly correlate to how strong of a statement we can make about the efficiency of mass transfer. So if these error bars on the masses decrease, we get much tighter constraints on the mass transfer efficiency. That's one thing. And then there's also, if we have, of course, more of these stars detected, we can have a bigger sample, and that improves a lot of things. But what I'd be interested in is looking at, let's say, the selection effects for these stars, because all of these stars in the sample currently have a very extreme mass ratio, where the accretor is much, much more massive than the strip star. And not also in the same figure, actually, you can see in color that the stars at the top with more extreme mass ratios are ones with stronger constraints on this efficiency. And so these stars are the most interesting. They should be the hardest to find, and yet these are the only ones that we see here, which is interesting. And I'm not sure if this makes this finding even stronger, that all of these stars should have had very conservative accretion, or what happens to the other stars that should be at the bottom here. Yeah, there's a lot of cool observations I think that could be done to improve our understanding here.
Hi, this is Doug Guys again. Sorry to dominate questions. I was very intrigued by your suggestion that viscous accretion disk might be a way to handle the angular momentum problem. Could you explain how that might work?
Right. This is by work by Pachynski in the 90s, for example. But they, and I haven't gone in too much into detail into exactly how these papers propose this process to work. But from what I understand, if you have an accretion disk, this accretion disk can first put back angular momentum into the orbit instead of just putting it onto the companion star. And it can handle accretion such that this companion star keeps accreting rather than it having to leave away. And so there's I hope I can refer you to these papers if you want to know more about that. But this seems to be a promising explanation for how this mass transfer can be so efficient.
Thanks, Thibault. Any additional remark to our speaker or questions again? If not, I need to pass some things that Lida showed in the chat. If I don't know if you have seen it, but she recalls that, of course, don't forget. Okay, Dietrich, just let me finish. Don't forget to put your abstract, of course, on those on the Massive Star newsletter that I assume everybody knows. And I will let Dietrich ask his question while I will put on the chat so that everybody can see the link where you can post the abstract. So don't forget to post it for the whole Massive Star community. Anything that you have, or also any meetings that you organize, don't forget to post everything there. Dietrich.
Very much. I'm a bit slow thinker. Very interesting, very fascinating talk. How much time does it take? How long does this mass transfer phase last? And what are the chances to observe a star in the act?
That depends on the timescales, thermal timescales of both stars, of the donor star specifically. But it is actually quite common to see these stars during the mass transfer process. Specifically, these are usually algols, and if I had to give you a number, it would be like let's say 10,000 or 100,000 years, depending on the mass of the star. But algals are definitely quite commonly observed, and they show us in a star system in contact that is currently overflowing its Roche-lobe and transferring mass to the companion star.
Thanks, Thibault. Last question? No, so let me thank the two speakers again, Ilfa and Thibault.
Thank you.
And of course, let me recall that the working group of Active B-Star is regularly organizing seminars, and the next one will be again on very specific objects, which are the X-ray binaries. So again, we will probably hear about mass transfer and stuff like that. This will be in February, so stay tuned. We will have information about that soon. In the meantime, of course, let me wish all of you a very great Christmas and New Year already. Time really flies very fast, so have fun. I hope everybody will enjoy the end of the year. Bye bye, and thanks a lot to Thibault and Ilfa again.
Thank you very much. Merry Christmas.